One of the things that's really interesting regarding Euclidean geometry and non-Euclidean geometry is that you'll notice that in Euclidean geometry and non-Euclidean geometry, parallel lines do not intersect. Now, skewed lines like this, they intersect. But if you can also have perpendicular lines that intersect. Now, the interesting thing that we think about is that when we see these partial or discrete graphs of linear combinations, you'll notice that we're actually using line segments. So, line segments are partial sections of a line. Sections by themselves, or segments, are in fact partial, but not sections, but segments. But anyway, so line segments can be graphed to show skewed lines, or and this could be in a three-dimensional XYZ graph. If you were to add an extra vector, it would essentially you could say that that's perpendicular, which is interesting in 2 dimensions. But one of the things that's really cool about this is that we actually define a line as in math or geometry as being continuous as one of its many traits or properties. So that means that this side goes on for infinity, and this side goes on for infinity. Now, one of the things that I was thinking about that I think is interesting is, what if, given that parallel lines never intersect, we had a version of geometry where that axiom does not apply. Now, we can't conceptualize this in our world, which is interesting considering that we can state it. So just because we can state something doesn't necessarily in our world mean that it can occur or that it exists in the physical realm. Now, interestingly enough, we can look at when we draw something in art using perspective, we will always go to the horizon line. Now, when you draw parallel lines in perspective, you'll notice that they do meet at the horizon line, or at least you would assume. But that's the thing, is we can draw the horizon line, and yet the horizon line doesn't really exist, because these lines are going to continue forever, such that this gap gets smaller and smaller, and yet incrementally getting smaller, those two parallel lines, the way that our mind interprets it, don't actually meet. But how can this be a representation of parallel lines if they actually do meet when we draw it in perspective in art, and yet the horizon line is infinity, but we can draw it in a discrete way? Now, these are interesting ways to look at parallel lines. But what if the axiom for Euclidean, a form of non-Euclidean geometry, or that doesn't exist yet, you were to say that, given the logic of the situation, parallel lines do meet, either at infinity or before infinity, or at a transcendental number past infinity. Now, that's an interesting thought to have when you're thinking about math. And it's actually a paradox, even though we don't really stress over the fact that this exists, it's a strange, odd perception that we have that any two intersecting lines can in fact meet if they are parallel, such that we would see skewed lines as being parallel. It's a little strange. And this relates to the realism of the reality we live in, as far as how we associate parallel lines with the perspective of things we see in reality. So perhaps the problem is not the reality of the lines or the perspective, but rather the reality of how we perceive reality. Such that if we were to change that axiom that parallel lines never meet in a geometry that we use, such that those parallel lines do actually meet at any one point or even more than one point, then that's interesting. And one of the things about graphing a line is that you can only graph a line segment. Now, the thing that's strange about that is that when you think about an actual line, the concept, lines are infinite in length. So we don't know if they curve or veer off at any given point in the future, given that we only have the segment. Now, this is interesting when we think about sets, such that if you think about it like a line in a number system, the spaces on the line correspond in a one-to-one relationship with the numbers. Now, in set theory, we will oftentimes show a pattern by putting parentheses around three numbers separated by a comma, by commas. And so we'll put I think it's a ellipses or whatever it is, 3 periods to create a continuous, basically to say that the pattern continues in such a way. Now, what's interesting about that is that much like a line that curves at some random point, how do we know that this pattern of numbers or this sequence or series, that it will actually never veer off from the given pattern? And so the other thing we can ask ourselves is, what if, rather than simply saying 1, 2, 3 is a pattern and then counting upwards, what if this was indicative of an alternative pattern than to a simple pattern of addition or counting the whole numbers? Now, that's interesting, and honestly, though there's some paradoxes in the way that we take three-dimensional things in some instances and two-dimensional in others, one-dimensional, and we bring them down into this two-dimensional dimension such that we can draw them on paper, and our mind can interpret the concepts, even though the concepts themselves don't necessarily make valid sense. Now, that's an interesting concept logically, to actually ask yourself, can we have a non-Euclidean form of geometry such that that non-Euclidean geometry involves two parallel lines that do actually meet at some given point or more than some given point? And can we actually have a function that produces, or an algorithm that produces, an infinite line? Or if a line is truly infinite and continues to infinity on both sides, can we only represent that symbolically versus being able to draw the actual line? So my preponderance of this would be such that when you think about a line, you're not actually thinking about a line. You're only able to compute with your mind a line segment, or a line that's symbolically representational of a line such as this.